My name is Ali Kujuri, and I'm a adjunct professor here at the Engineering Science Department. Let me, on behalf of the Engineering Science Department and the School of Science and Technology, I would like to welcome you all to be attending this second lecture of the series of the academic year. I would like to thank Agilent Technologies for sponsoring this series since the start. And before I start introducing our guest speaker for today, let me mention that 2 weeks from now, October the 1st, we have, by the way, this is Mr. Sorry, I mean, when I asked him recently, he said, no, just Mr. Mike Powers is in fact, engineering scientist at Agilent Technologies. And his talk will be on the MEMS in the 21st century. MEMS is micro-electromechanical systems that in fact use these days for a lot of in a lot of our devices. Very common. For the talk today, we have Professor Venkat Anantram from the Electrical Engineering and Computer Science UC Berkeley. Who will be presenting the talk titled Breaking the Error Floor of the LDPC. I don't want to go through the acronym because he's going to talk about it. But Dr. Venkat Anantram received a Bachelor of Technology in Electronics in 1980 from the Indian Institute of Technology, Madras, India. He also earned his MA and C Philosophy degrees in mathematics and Master of Science and PhD degrees in electrical engineering in 1983, 84, 82, and 86 respectively. Anantram was on the faculty of School of Electrical Engineering at Cornell University, and he has been a faculty of UC Berkeley since 1994. Anantram received the Philips India Medal and President of India Gold Medal. That's good, all right. From IIT Madras in 1980, and National Science Foundation Presidential Young Investigator Award during the period of 1988 to 93. He is a co-recipient of the 1998 Prize Paper Award of the IEEE Information Theory Society and a co-recipient of the 2000 Stephen Rice Prize Paper Award of the IEEE Communication Theory Society. He received the Distinguished Alumnus Award from the IEEE Madras in 2008. Anantram is a fellow of IEEE. So here he is.
Are you using a microphone? Or is this loud enough? I'm pretty loud, so great. Thank you very much for that very nice introduction. It's a real pleasure to be here at Sonoma State and to deliver this talk on LDPC codes. See if I can figure out how this works. So this is to go ahead? Great, okay. So the LDPC...
There is a laser pointer there.
Oh, there's one here too?
Below.
Okay. Oops, sorry.
Press it again.
Press it again?
Yeah. Top one maybe. Yeah.
Okay, excellent. All right, great. Thank you. LDPC stands for Low Density Parity Check Codes. This is one of the two major classes of error correcting codes that are popular in applications today and also in various standards. What this talk is about is a project that has been going on for many years at Berkeley, of which a group of faculty is involved. I know several students. I'm just one of the players in this project. And the project is to address the techniques for improving the performance of these codes in applications that require extremely low bit error rates. These are applications like magnetic recording, and specifically this talk is going to be about gigabit Ethernet standard. And the punchline of the talk is that through a very, certainly a very pleasant and enjoyable mix of theory and practice, we have made substantial contributions to basically improve the state of the art, commercial state of the art in this area. So I want to develop the story by setting the stage and then also indicating where the theory comes in and how the practice came in, and just sort of give you a high-level overview of this several-year project. Right here are the main collaborators on the work that I'm going to be presenting. Let me tell you who all these guys are. So Zhenya Zhang is a student, was a student. He's now going to be joining the faculty at the University of Michigan at Ann Arbor as a tenure-track assistant professor. Zhenya is an expert in hardware VLSI, and much of the VLSI aspects of what I'm going to talk about were actually implemented by him as part of his PhD thesis. If he was here, I would request you to ask all questions regarding VLSI to him, but he's not around. Bora Nikolic is one of my colleagues, a faculty at UC Berkeley for several years. His area of expertise includes communication architectures, hardware, VLSI, etc. He has co-written a classic book in the area, which is widely used in various courses. Martin Wainwright is one of my colleagues also. He's a coding theorist. He also works in the Department of Statistics. So much of the theoretical work, aspects of this project from the faculty side were contributed by him and me. Lara Dolachik is my student. She did a lot of the theoretical aspects of the work presented here as part of her PhD thesis. Both Lara and Zhenya, incidentally, were awarded best thesis prizes at UC Berkeley for their work. So this work is really being received quite well by our colleagues. Lara has spent 2 years as a postdoc at MIT, and she's now going to join UCLA as a tenure-track assistant professor. So I want to make sure that all the credit is given here, because I'm just one player in this story. So these are all several people, lots of brains brought into this. This work is in the area of communications, and here is the god of communications, Claude Shannon, one of the greatest scientists of the 20th century, and becoming recognized more and more. Actually, he is not yet spoken of in the kinds of tones in which he should be by the world at large, but his impact on our life is truly profound. So in particular, he wrote a paper called The Mathematical Theory of Communications, which is available in the Bell System Technical Journal, and it has been called the Magna Carta of the Communication Age. He basically defined the communication problem of communicating information in an abstract way, which allowed us to think about it systematically. And the framework that we work with in order to deal with these practical communication problems arises from the thinking of Shannon. Basically, Shannon's view of communications has been successful because it abstracts away the idea of the meaning of what is being communicated from the concept of the uncertainty of what is being communicated. He ignores the notion of meaning, so it's not really a question of whether what is communicated means to you, whether something that is being communicated means something to you or doesn't mean something to you. What really matters is that after somebody has communicated something to you, you used to be uncertain about what was going to be said, and now you're certain, in effect. So communication is conceptualized as a matter of making a choice. Now, typically channels over which people talk are noisy. That is true, of course, for wireless communication channels, radio channels of various sorts, in fact, most channels that we deal with, although I guess optical communication channels are pretty close to being noise-free. They have different kinds of issues having to do with packet drops and so on. So you have a noisy communication channel. The basic problem is that if somebody is trying to resolve uncertainty for you, they send you some datum, and what you see may be a different or a corrupted version of the datum that they sent you. You can just think of a point inside some big set. So that's what this picture represents. This red ball is a big set. You can actually think of it as a representation of some power-limited set of waveforms, if you like. That's what it is meant to represent. A person would like to send you a specific waveform, but when it comes over a noisy medium, that waveform gets corrupted by noise, and so you don't get exactly what the transmitter sent. You get some kind of thing that is close to what the transmitter sent. The basic idea of coding is you solve this problem by not allowing the transmitter to use all possible waveforms inside the big red ball, but only allow the transmitter to use the centers of these small spheres, in effect, noise spheres. So then what the receiver can do when he sees a point is he can get a pretty good idea of which of these green balls it came from, and so he can figure out what the center was. That's basically the idea behind coding. So you can think of it as bin packing, so you have some big bin inside which you try to pack balls. AWGN here stands for Additive Wide Gaussian Noise Channel. That is a traditional channel model that people discuss for communication. The idea is that the noise, being an aggregate of a lot of different kinds of influences through the central limit theorem, can be modeled as being a Gaussian process. I'm trying to cover all audiences in this. So if you have not seen the central limit theorem before, that's one of the reasons why the Gaussian distribution is an important distribution. Is that there is a theorem that tells you that if you have effects that come from a large number of small perturbations, then the distribution is very often close to Gaussian. And the noise generally tends to act by adding on to the waveform that was transmitted. The white basically represents the fact that the spectrum of the noise is more or less flat. The energy in the noise is more or less flat over the spectrum of the communication. That's a traditional kind of model which works well in lots of cases. This picture is meant to illustrate that. Now, what Shannon did was he studied a mathematical model for this additive wide Gaussian noise channel, among other channels, and he came up with theoretical bounds as to how much uncertainty can be resolved over such channels. So these are measured in terms of data rates per unit bandwidth of the channel, bits per second per hertz. You can also measure them in terms of data rates per use of the channel, because the bandwidth available to the channel can be converted intuitively into a number of degrees of freedom. You can measure it in terms of the amount bits per second that you can send, so bits per use of a degree of freedom that you can send over the channel. This picture is meant to illustrate the history of what happened in this area from a theoretical point of view. You don't need to go into all the details. I have several slides, just giving you an overview picture. The black curve here is Shannon's capacity bound. In effect, Shannon proved a theorem telling you cannot go to the left of this black curve. And if you don't use coding at all, then you get this blue curve which is called uncoded. Shannon's theorem was proved in 1948. If you think about his baseline as being 0 dB, that's what you'd like to get at. And this gives you some idea of the historical progress towards this goal. So people kept inventing better and better codes, but there was some kind of a phase transition in what people were able to do in 1993 through the invention of a particular kind of code called a turbo code. This was actually invented by a pair of physicists, which is kind of unfortunate from the point of view of engineers. It's Claude Berru and Glavieu, I don't know his first name. Glavieu unfortunately died prematurely, but Berru is now got a lot of credit for his work, and recently was elected as a member of the French Academy of Sciences and so on. Academy Française and so on. So this was a so-called turbo code. In fact, historically, when these codes were presented, there was also a student called Titima Shima. I'll give exact references in the next slide. When this was presented, people did not believe this result because it was so much better than preceding results. But then they were able to reproduce the results, and finally they agreed that it worked. Then it was discovered that already in the 1960s, Bob Gallagher, the famous communication theorist from MIT, had invented something called low-density parity check codes in his thesis. People had just ignored it for decades, and they turned out to be essentially as good as the turbo codes. And then the LDPC codes have been studied and optimized quite a bit. I think this is still the benchmark for how close people can get to the Shannon limit. And this is work of Tom Richardson, Seiyung Chung, and I'm not sure if I remember all the authors. So there are basically two classes of codes that competed in terms of getting, these are what are called modern codes. The turbo codes and the low density parity check codes. And I think most people you talk to today will agree that low density parity check codes, at least currently, seem to have won the battle. But this is, if you talk to persons who work on turbo codes, they will not agree, obviously. I mean, it's still a battle in some sense. Turbo codes, both of them basically involve some intelligent way of introducing randomness into the code structure. So this is the original paper that was presented at a conference that presented the turbo codes. And low-density parity check codes actually go back all the way to the work of Gallagher, 30 years before that, just that people ignore it. So this is roughly the structure of turbo codes. I won't say much about it. I think many of us will find it easy to understand what a convolutional code is. A convolutional code basically works as a finite state machine. Coding is a matter of introducing redundancy. So the way a convolutional code works is you put the bits in, the message bits, and you create more parity check bits. And you create them by some kind of shift register implementation, where you just read off certain linear combinations of the incoming bits. That's what a convolutional code works like. The idea behind turbo codes was to work with multiple convolutional codes with some kind of permutation for the message bits into one of the codes, and then to use a mechanism for each convolutional code helping the other one back and forth, passing partial decoding so as to get improvements. That's sort of a rough picture. And I explained the word turbo because it's sort of like a turbo jet. You sort of put back partially processed fuel, so to speak, back into the engine. That's why the word turbo comes from. Low-density parity check codes basically work by setting up a bunch of checks for the message bits that you want to send. A check is just some kind of constraint that you've tried to define, it's a linear combination that you define, and then the decoder is going to check whether this linear condition is satisfied after the noise, and thereby try to correct and figure out what was actually said. And the key thing in the low-density parity check codes is that the decoding algorithm has the same kind of structure. In fact, Gallagher had already invented that in 1960s, which is that the way the decoding works is that the checks and the bits, so to speak, send partial information back and forth. So this turbo structure was already buried inside Gallagher's thinking decades ago. I'm going to focus on low-density parity check codes throughout my talk, so that picture will be kind of important to us. That's called the message passing picture. We'll say more about that as we go along. Okay, so these kinds of talks are sort of de rigueur in engineering presentations. This is the reality of the world we live in, the information revolution. Everything is growing exponentially. I'm talking about the communication space, so this is just giving you some flavor of how technology has been advancing. The red lines represent wired communication systems, ISDN, ADSL, so digital subscriber line, various things, VDSL, various sorts. Here you can see the time axis. And these represent, blue line represents progress in the wireless space. So a point I want to make is, as we all know, is that there are many different technologies that have enabled this, not just communication technologies. A lot of things in VLSI, a lot of actually manufacturing capabilities, and in fact I would even argue that the entrepreneurial infrastructure here has been a driver in many ways. So the VC culture, etc., should also be credited. It's not just technology, it's also infrastructural kind of aspects. But in the communication side, there have been lots of enabling technologies, and in that space of enabling technologies of a communication sort, codes are also playing a strong role. And that's just the focus on this talk is entirely on the codes. So just this purpose of this slide is then to tell you that, okay, codes also play a role in the story. Right? Many things play a role, but good codes also play a role. So I'm going to focus entirely on the project that we developed, that we have been working on for the past, I would say, almost a decade now. And the general vision is that we need to go across all layers of the stack in the process of building chips in order to come up with good designs. So there are people who work at many levels of the food chain. There are very theoretical people who develop algorithms. And then the algorithms need to somehow be mapped at a conceptual level into, I guess, data structures, aspects having to do with choices as to certain parameters in the algorithm, like quantization levels and so on and so forth. You might call that algorithm realization. It's also somewhat theoretical business. Then there's a question of actually mapping these algorithms onto some kind of architecture to build a chip. And finally, there's a question of actually implementing on the chip, right? It's physical design, place and route, etc. The hardware architecture requires decisions as to how to use resources like memory, wiring bandwidth, how to sort of set up the algorithm within the hardware. This is sort of the general design flow. And improvements come when you introduce feedback into this picture. So implementation constraints might tell you what to do to modify your architectural design. They could also give you some insights into how to make different choices in realizations, like word length choices, etc. But I'm going to describe aspects of this that entered our thinking in the course of our project. I mean, this is not just wheel spinning. This is giving you some flavor of the kinds of things that went on in the project that eventually resulted in beating the state of the art for gigabit Ethernet decoder chips. And in fact, they may lead you all the way to modifying the algorithms itself. And in fact, that's what finally we ended up doing, is actually figuring out how to modify the original theory in order to meet the needs of the architecture design. So here now is the outline of my talk. Okay, so that was just sort of setting the stage. So I'm going to describe for you what the message passing decoder for a low density parity check code looks like. In effect, understanding these codes itself is very difficult because these codes, in the kinds of applications we are interested in, need to work at very low bit error rates. So finding out actually what are the theoretical aspects of the code that control its performance at low bit error rates is very difficult to do. First of all, it's hard to do theoretically because the theoretical properties of the decoding algorithms for these codes are not understood to this day. They correspond to certain kinds of nonlinear dynamical systems which have buried in them periodic phenomena, chaos, etc., which people don't understand. But it's also very difficult to do using simulation because we are working at error probabilities which are so low, like 10 to the minus 14, 10 to the minus 15, that you cannot do simulation at a reasonable time and get adequate confidence on the estimates. So we had to actually go through hardware emulation even to work with the error characterizations. The hardware was used in order to aid the theory, in order to, in effect, speed up simulation by working with emulation. Then, having discovered some aspects of the code, we then basically use that to guide the architecture and then to guide the theory going backwards. So that's sort of the design flow of research that happened over all these years. There have been other students who have been involved in this research. One of them I should mention particularly is Englin Yo, who is now a colleague working at Marvell Technologies, but I didn't put that was, but that was several years ago. So here's what a typical communication system looks like. I mean, there's a data source. The transmitter basically is going to send the information over the channel, and the receiver tries to figure out what the data source is. So the standard picture that you will see in any communications source. Typically, the data source is encoded into a sequence of bits through some kind of some compression scheme. And these bits are modulated onto a waveform. Modulation means that, for instance, you might set the level of the waveform. If it's a +1, you might decide to send it with amplitude A. If it's -1, you might decide to send it with amplitude -A. That's a process of modulation. Then the channel is usually noisy, and the receiver has to undo whatever is being done by the transmitter. Typical, this is what I guess Gallagher calls as a communication theorist's coat of arms. Right? It's like going out into battle and this is a coat of arms. System performance is usually described through some graph which tells you the bit error rate as a function of the signal to noise ratio. Now, when you introduce channel coding, that is this picture that I showed in the third slide, where you try to do this bin packing, the beauty of channel coding is that it gives you something called coding gain. You have to go through the mathematics to actually see that that happens. In effect, what happens is that because, as you separate out these points, even though you lose something in the rate, because of these distances become larger, you're able to gain in the error probability sufficiently to make up for that rate. So you have to do the math to figure that out. It's called coding gain. And in fact, you end up getting the same kinds of bit error rates for lower signal-to-noise ratios. And Shannon has told us theoretically how far you can push this curve to the left. That's a Shannon limit in effect. It tells us how much you can go to the left. And then all of the practical implementations have been, practical and research has been on trying to arrive at things that are close to the Shannon limit. I don't want to oversimplify because, as I said in the beginning, this is just the additive white Gaussian noise channel. Right? Real communication channels are incredibly varied. Wireless communication channels are far different in flavor, for instance, because of the phenomenon of fading and so on. And the different kinds of physical nature of the communication channel might lead to completely different models. For instance, optical communication systems need to worry about things like phase. They're based on energy rather than magnitude and so on. So every channel has its own flavor to it, and its own coding problems, and its own goal, etc., etc. So a very, very big area. But I'm just focusing on the AWG. Now, low latency badly checked code, the kinds of codes I'm going to discuss, conceptually it's constructed in the following way. There are some message bits that the transmitter would like to communicate. In this picture, there are 6 bits. And because it's going to be communicated over a noisy channel, you try to introduce some redundancy into what you actually communicate. The redundancy is introduced by adding some more bits which obey certain linear relations with respect to the message bits. This check, for instance, would then be, in this picture, it would be the sum of bit 1, bit 3, and bit 5. Binary sum. So the receiver is going to receive noisy versions of bit 1, bit 3, bit 5, and also a noisy version of check 1. Because what you transmit is the 6 bits and the 4 checks. So the receiver can then try to figure out whether this relation is satisfied or not, and thereby try to sort of correct the noisy bits in order to figure out what was originally transmitted. That's the idea of coding. So you can set up this, you can also describe this graph. This graph is called a Tanner graph representation through a matrix. So here the matrix has got 4 rows corresponding to 4 checks, 6 columns corresponding to 6 bits. You place 1s in the places where you have edges. So you can think of this as telling you that check 1 should be bit 1 plus bit 3 plus bit 5. All this is done at the transmitter. The receiver is going to get corrupted versions of the 6 bits and the 4 checks. So now these relations may no longer be satisfied. It's got to figure out some way of figuring out what the most likely thing that happened was. That's communication. I mean, it's not rocket science at this level of description, but actually getting good performance is important.
Yeah, question. Here, out of the 10 bits that are transmitted, 4 of the things are going to be the extra stuff that we have to send. So we are talking about 4 divided by total of 10, about like at least like 40.
That's right.
40% is loss of the thing.
Yeah, so that's a reduction of rate. Yeah.
Yeah. So.
But the gain you get from that is that the error probability gets much lower.
Okay.
That's precisely the concept of coding gain.
So you are assuming that here we use really broadband since, let's say if you are using fiber or whatever, transmission time and so on doesn't matter, so we can live with the extra stuff then, right?
There's a trade-off between power and bandwidth in effect, and the kinds of choices you make as to which rate you would work with depends on what that trade-off would be. So if you are severely bandwidth constrained and power was not an issue, then you might not want to use this kind of coding.
Yeah. Because when you look at this one as a physical layer, as soon as you want to talk about the application or other, check things and so on that you have in the layers of the communication, and those are all going to be added to this thing and so on.
So in the overall design, that is also a very important point, because one way of recovering from errors is to push the problem up to higher layers. So you might just decide that whenever an error occurs, you just ask for retransmission, for instance. So there are also trade-offs in terms of how aggressive you want to be in the coding and how much of the problem you want to push to higher layers. The overall design always has those aspects to it. However, in terms of the problem that we addressed, we arrived at this problem post facto, in the sense that, for instance, in the gigabit Ethernet standard, a particular kind of code has already been chosen. And now our problem is to try to optimize that code. That's sort of how we arrived at the problem.
So what is low density? I'm trying to put that in.
Very good question. The point is that this parity check matrix typically will be much larger than what you see here. So it might have, say, in our case, it has about 2,000. It has 1,009. The exact numbers. It has the order of 2,000 columns and a few hundred rows. So low density really means that the number of ones you see is very sparse relative to the size of the matrix. But I mean, there's a formal definition, but the definition, to make a mathematical definition, it has to be done asymptotically as the size of the code goes to infinity. And then in effect you say that the number of ones is only linear, so you might say it's a constant. You have different definitions.
And that's going to lower the power. I mean, if the number of ones are lower, is it the idea?
No, actually, the reason it's good in some sense is it's good from the point of view of complexity of decoding. For one thing, you send few messages. And certainly the complexity of encoding also. So that's the main kind of reason. The performance of the code itself. First of all, I mean, the question of whether it's low density or not, in a sense, it depends on what kind of bases you use to represent the code. Because these are binary objects, and you can think of them in linear algebra terms by forming linear combinations of columns, etc. So something that looks like a low density matrix might look like non-low density matrix in another basis. So there's nothing really intrinsic about it, but the sort of motivation for it comes from the simplicity of this representation, and you decode usually within a particular representation. You having chosen a basis, so you're passing few messages back and forth. So really, we want to think of it as a complexity related issue. So this is in effect how the encoding process would work. You know, you have, let's say that you have a bit. So if you're using binary phase shift key modulation, which is basically pulse amplitude modulation, you might represent 1 as -1 and 0 as +1. So every single bit we think of as being corrupted by additive white Gaussian noise. So the level +1 is corrupted into a Gaussian received value which is Gaussian with some variance centered around 1. Level -1 is received as at some level which has Gaussian distribution centered at -1. So the receiver then makes a decision. He might put a threshold in the middle here and decide whether it was +1 or -1. That's a hard decision. Right? That's a typical picture for a communication. Now, on the other hand, you might also want to make soft decisions where you sort of have a finer granularity with which you break this observed value up into a bigger granularity, a finer granularity than just +or -1. Now, the way this low-density parity check code decoding algorithm works, essentially the ideas of Gallagher, rediscovered in the Togo coding story, is that there are messages passed between the bits and the check. So the bits have been sent by the transmitter using this process. So for instance, let's say something like bit 3. Bit 3 was either a 1 or a 0. If it happened to be 1, then the transmitter would have sent a -1, and then there will be some level that got received here. So that's what one means by the prior beliefs. Right? There'll be some prior beliefs about the bits. Now, what one does is one just then goes through one sort of figures out whether the check conditions are satisfied. So these bits send these messages, can be thought of as sending their prior beliefs to the checks. So the checks sort of decide whether the conditions are satisfied. So they try to enforce the parity constraints, and then they send back messages to the bits that they are connected to, telling them, well, this is what I think you should be. So each check is telling the bits what it thinks it should be. Now the bits work with the prior information together with what the checks send, and then they send another level of stuff to the checks, and then this sends it back to the bits, and basically that's how it goes. So this goes on for a few stages, typically 200 stages in a chip. And then at the end, you just make a decision. And the hope is that this sort of cleans up the noise, and you get a better and better decision because you're looking more and more into the graph. There are no theorems for kinds of codes that people use. This is one of the big problems in this area. There are theorems if the graph looks like a tree, which is not a very good code, then you can prove that this process converges. But for the kinds of codes that people use, they tend to work, but to this day there's not sufficient understanding about why they work. And that's one of the challenges for the theory. The basic idea of message passing is in this one graph. This is the most mathematical graph that I have, the most mathematical slide. But this is just to illustrate that the kind of algorithm that is being used is actually a wide range of applicability. If one goes to the theory, one sees that this algorithm that is used in this turbo coding decoding or in the LDPC decoding is an instance of the same kinds of algorithms that people have known in other areas. For instance, the Kalman filter actually can be viewed as an example of this kind of algorithm. The various kinds of algorithms in hidden Markov model theory, BCGR algorithm can be viewed as an example of this. Algorithms that are used in expert systems by people in artificial intelligence can also be viewed as an instance of this. Basically a generic way of estimation. And the essential idea is that you want to somehow have some collection of entities which are jointly observe something and want to arrive at some kind of posterior probability estimate. And what you do is they sort of help each other. So if you take some node, R, you can think of him as having observed something. So he has some kind of local function, which is a function of the variables that are at the node. So he has certain variables. Just think of it abstractly. Some variables denoted by x sub r. He has some function, alpha sub r of x sub r. He wants to help the node u to get a better picture of what's really going on. The way he does that is he takes the stuff that the people other than you have told him about what is going on. So these are these mu, for instance, t1r, there's a message mu t1r. It is a function of the variables that are common to r and to t1. So he takes all the messages from people other than you, combines them with his own picture of the world, and then sort of marginalizes out over all the variables other than the one he shares with you, and sends a message forward. That is the basic message passing algorithm. Everybody is doing this completely asynchronously. Mental picture is just think of a graph. There are 1,000 nodes, and it's connected in some way. At some time, any node wakes up and says, "Oh, what is the most recent message I heard from these 20 guys who are connected to me, other than this 21st guy that I want to talk to?" I take all those, I combine them with my picture of the world, I send it forward to this guy, I go back to sleep. This is the algorithm. And if this goes on long enough, then it seems in a lot of practical situations it seems to give rise to the global solution, the best possible estimate, as if everybody was in the same place. This seems to work. Now, in the sense, in the case of trees, it's been proved to work. That is, if there are no cycles in the graph. If there's one cycle, then it's proved to work in some cases. But most of the graphs have lots of cycles, and there are no theorems. But this is the nature of what's going on. You know, the checks and the bits, they've got some picture of the world, and they just sort of exchange their picture. They do it often enough. It looks as if you've got the globally optimal estimate, maybe the maximum likelihood estimate. Looks like that. It's not entirely true. In fact, where we address this issue is that because it's not entirely true, we've got to make it closer to being true. And that's what our project's all about. So when you want to implement this sort of message passing algorithm, you can think about the bit nodes as having being some kind of entity, the check nodes as being some kind of entity. Bit nodes have some kind of prior belief, and then they send a message to the checks. And then the check nodes compute something. They, of course, get messages from a lot of bit nodes, and then they send messages to the various bit nodes that they're connected to. So you can think of various entities which are like bit nodes and check nodes conceptually, and they're talking to each other along the structure of the standard graph. Now we come to the practical issues. Messages are saturated and quantized for storage and processing. They're not really real-valued numbers. And as a result, numerical errors arise, etc. So the real performance in practice is dependent on all these things. Now you see here something called the log tan hyperbolic function. There's no need to worry about what that is. It turns out that in the case of the Aladdin-White Gaussian noise channel, when you write down the equations, you have to work with the log tan hyperbolic function. It's not very surprising. There's an e to the minus x squared floating around. So if you do the calculation for posterior distributions, you'll start seeing things like e to the minus x plus e to the plus x divided by 2, etc. So you can expect hyperbolic tangents to show up, and they do show up. Of course, since everything is done at a quantized level, you only approximate this log tan hyperbolic. So now then there's various kinds of of architectural issues that would come up in terms of implementing this kind of message passing algorithm. One extreme might be to imagine a fully parallel architecture where there is an individual entity for every one of the conceptual entities in the algorithm. The other would be to think of a serial architecture, but that would require a lot of motion between memory and the entities that. So this guy is like a bit entity and a check entity, but they've got to keep passing things back and forth because they play different roles at different times. So that's kind of complicated. So there's a trade-off between different kinds of architecture. So all this entered the thinking of the VLSI folks. I have about 15 minutes, is that, or less? 10 minutes.
Yeah, let's leave the last 5 minutes for
Yeah. I mean, I sort of said a lot of things I want to say, so I'll sort of go through rather quickly some of these trade-offs because I think I gave the big picture, and that's all I wanted to do. So the theory tells us that randomly constructed codes get close to the Shannon limit, but we need explicit constructions that get close to the Shannon limit. Now, the low density parity check codes, turbo codes, etc., they are very, very good. They get close to the Shannon limit. But if you start to impose structure on them, that is, if you start to work with codes that are implementable in some decent way using kinds of hardware architecture that are currently, hardware capabilities that are currently available, then you find that you can't really get all the way to the Shannon limit. You get some kind of a problem which occurs beyond what you might call moderate bit error rates. So this is really the problem that we address. I'm going to discuss it entirely in the context of the standard for the so-called Reed-Solomon based low density parity check code, that is the standard for gigabit Ethernet. It's an example of a structured code. Those codes are used because they have some kind of a structure within the parity check matrix that allows for good hardware choices. Those kinds of codes end up having problems in that when you get beyond a certain moderate bit error rate, so something like in this picture it's 10 to the minus 6, but this is for a different code, then all of a sudden something starts to happen to the performance which is called an error floor behavior. That is, the performance no longer starts behaving as good as you would like it to be, but it starts to degenerate. So one question is, this is only at about 10 to the minus 6, but if you go deeper, then the problems become, what is actually causing this phenomenon, and how do you get rid of this phenomenon? So that's what we. So we approach this first for the Reed-Solomon based LDPC codes for gigabit Ethernet through first this emulation paradigm where we actually just emulate the code. We run it on hardware. And we try to find out what causes this error flow phenomenon. So I gave you this picture with this highly optimized LDPC code which got all the way down to the Shannon limit. But those highly optimized codes are not practically implementable. So there's this kind of a trade-off that we have to make. So this emulation platform is emulation is done on something called the Berkeley Emulation Engine. This is an FPGA-based platform that has been developed, actually developed originally by Bob Brodesson at the Berkeley Wireless Research Center. It's used for lots of different things. And there is, in fact, a direct way of mapping Simulink code onto this implementation. So that was done by Lara and Jelia in order to actually try to identify what causes this error flow. Now we're working currently with the B2 platform. I think maybe they're going to the next level already. And this is sort of some schematic of how it works. So you do the emulation and then you change the AWG and you gather data, etc. So these are just schematic pictures. What we find is that there are two kinds of errors. There are actually the kind of problems that occur in this error flow region. There are errors due to oscillations, and then there are what we call absorbing errors. Oscillation-based errors are errors where the bits, so you send a certain bit configuration. We are in control of the situation. So we send a certain bit configuration. It gets corrupted by noise, and then we run the decoding algorithm. We try to see what went wrong. In the oscillation errors, the places where you have errors, they tend to sort of increase in cardinality and decrease and go back and forth. In the absorbing things, the places where you have errors, they stabilize, but they stabilize into some kind of particular states, which we call absorbing states. So we have actually, in our project, we figured out different ways of solving both these kinds of problems. So here is uncoded performance. if you have really unusually high error flow, so this, I mean, the LDPC code is doing its thing. It's doing its beautiful thing of using message passing in order to try to get something that mimics the theory of that random codes are good. But then it runs into this unexpected problem where this error flow kicks in. When it's unusually high, it's usually caused by oscillations, but then ultimately it's determined by absorbing errors. This is sort of what we find. So we have to figure out ways of dealing with both these issues. So as I said, oscillations are due to propagation of numerical errors. We discovered basically that oscillations can be solved by making choices at the algorithm realization level, by making hardware, by word length and quantization choices. And then the absorbing choices, we eventually ended up solving them by making changes to the algorithm. So that's essentially the story. Since I'm getting to the last few minutes, I tell you where we're going. So I have a little bit more about how we solve this oscillation problem through these kinds of choices. But the heart of what I want to say is how we solve the absorbing error problem. So really the absorbing error problem story is kind of beautiful. If you look at code, the reason there's a certain sense in which a code can never be perfect. The idea being that the transmitter is sending one of various messages, and the receiver, I don't know which message the transmitter is sending. So if, unfortunately, it turned out that the noise corrupted the code word that the transmitter intended to send into some other code word, there's absolutely no way I can figure that out. Because for all I know, that's what he intended to send. So in a certain sense, what really controls the performance of codes is the fact that there are other code words around. It turns out though that for these low-density parity check codes, structured low-density parity check codes, there are some others, there are non-code word structures within the Tanner graph, combinatorial non-code word structures, which end up trapping the algorithm. That's what these absorbing errors are. So there are these things which have got smaller Hamming weight than the code words, a fewer number of ones, but which are aligned with the structure of the Tanner graph in such a way that the algorithm cannot get out of them. That's essentially what we discovered. And we call those absorbing sets. So here's a picture to illustrate the nature of that phenomenon. So imagine that the all zeros code word is transmitted. Then all the parity checks are then satisfied because you're just checking sum of zeros is 0. Now let's use hard decisions for simplicity of illustration. If a few bits are corrupted, then what will happen is that some checks will be set to 1. So that's sort of the picture of what needs to be set. Now, on the other hand, if from the point of view of the decoder, the bits that are corrupted and the checks that reveal that those bits are corrupted happen to have a configuration where each of these bits is connected to more satisfied than unsatisfied checks, then the bit doesn't seem to have enough evidence to want to change. So configurations within this Tanner graph, which have the property that, so you set up a certain configuration of 1s here. There are some checks that are, of course, revealing that this is bad news because you send all zeros. But each one of these guys might end up being connected to more guys who are happy than they're unhappy. And there turn out to be structures like this where the number of ones that have this property is got weight which is less than code words. These are what we call absorbing sets. And the exact structure of these, for the structured codes, we discovered them. This was one of the papers that Lara has written, using finite field theory, because these codes that we construct are based on Reed-Solomon codes and they involve various kinds of finite field math. So they had to classify using various kinds of techniques in finite field theory what these structures are. Existence of cycles also tends to reinforce incorrect bits, etc. So this is just to give you an illustration of that. Okay, now back to this oscillation business. So there are phenomena like clipping and quantization that take place in the practical implementation, which tend to lead to these kinds of oscillation algorithms. So one is you might have, when you define the prior likelihood, you just define it up to some numerical accuracy, so there you have quantization. Whenever you do things like summation, etc., also you end up having to clip values because you sum them together and then you have certain levels, some dynamic range, etc. Secondly, these kinds of functions, which theory tells you should be log tan hyperbolic, have to be approximated because you're working with some library, right? So all these things are issues. And one of the papers that we wrote, which solved the oscillation phenomena issues, basically came at the level of the algorithm realization story of this hierarchy. we discovered that if you change the quantization representation in the two parts, that is in the big node part and the check node part, you use different kinds of quantizations in those two parts, then you can get rid of this oscillation phenomenon. So this is a paper from 2007. Okay. We also discovered that if you modify the algorithm a little bit by replacing it, by eliminating the log time hyperbolic function and working with something called a min-sum approximation, then you get some improvements. Okay, now then we are left with the problem of the absorbing errors. So we are down to these funny structures which are somehow seem to be trapping us, and the question is how do we get rid of it? So there the ultimate sort of solution turned out to be a change in the algorithm. The idea is very simple. The idea basically is the following. Okay, here is the structure back again where there are some guys who are telling you that there's bad news, but the other guys, there are so many of them that they seem to be happy that you don't recognize as bad news. How do you handle that? Well, the guys who are telling you they're happy are basically lying, right? And the other guys are not. So you want to pay more attention to the guys who are not lying. Because, I mean, you have to recognize that and all that. So that's part of the story. But it turns out you can do that. All the details are given. So you just give more credit to the messages from the guys who are telling you that things are bad, less credit to the guys who are telling you that everything is hunky-dory. So in effect, what you do is you modify the algorithm. You change the message passing algorithm in order to make it some kind of weighted message passing algorithm. I mean, the high level it sounds like a simple idea. The question is how do you actually do this? So we ended up doing this, and this is the story. The error flow just completely vanishes. So after all those architectural choices about the quantization levels and all that, plus this idea of modifying the algorithm, the error flow just completely disappears. Now this all looks like it's theory, but we have to go and actually build this thing. So there's various kinds of choices that got done at the hardware level. Some of these I'm not even qualified to talk about. These are choices that were made largely by Genia and Bora as part of the implementation aspects of this project. So I'll just run through some of them. Basically, it's a question of how do you partition the parity check matrix, what kinds of decisions do you make for the wiring complexity. So our code actually is a 2048, that is base plus check is 2048, number of check nodes is 384. So that's the size. This is basically a standard for the gigabit Ethernet. So having made the right kinds of choices there from based on the architecture, the hardware constraints in terms of wiring complexity, etc. That is, choosing how to partition up the parity check matrix. In effect, one had to analyze what the various possibilities were, and it turned out that a good choice would be somewhere in the middle where you get. So here there are two graphs here. There's something called the area expansion factor, and here's a measure of the wiring complexity. So it turned out that for certain kinds of intermediate partitioning choices, we got pretty stable behavior over a wide range, so that's where we ended up making those choices. So then we implemented this, and here's a comparison of how different kinds of architectural choices would affect the performance. So if you had a 6-bit word length sum product algorithm, then this is what you would get. The red curve is what you would get. These are various VLSI metrics: area used, power dissipated, throughput, etc. And they're just telling you how they change as they made these choices. So area seems to go up, power goes down, throughput stays roughly the same. If you do the min-sum approximation, etc., you get slightly worse, but you get big improvements in area, power, and throughput. And now you do the two-step decoding. That is, you change you sort of change the quantization level of the two sides, then you get down.
When you talk about the throughput, is actual data, or does that include the coding bits?
Throughput is the actual data throughput, yeah. That means the actual message throughput.
And that includes the coding bits.
Yeah, I mean that's kind of as overhead. So it would be like the raw data rate multiplied by the rate of the code. That throughput is message bits per second, like you said. Include meaning it's accounted for correctly, is what I mean. That is in the sense that you're sending, you want to send actual message data at a certain rate. Those are the rates that are reported.
What I'm saying is, at the end of the day, what really matters is the data.
That's right, exactly. That's exactly what we're
That's
talking
what
about.
you're.
That's what we're showing.
Okay.
So we've also started, discussed how this scales against different clock frequencies, etc. So all this has been implemented. As I said, I'm not really the right person to be presenting this part of the work. I should also say the slides actually are prepared by Zhenya Zhang. They are part of his thesis, his interview talks which he gave in the process of getting his job in Michigan. So there's a bit of an emphasis here on the VLSI parts of it. But I told you the early parts of the story. They're the ones that the more theoretical members of this group were largely involved in. The punchline though is the following. A chip has been built. It's a 10 million transistor chip. Here's all the details. And let's see. So this is, for those of you who know about VLSI, you can go through all these numbers. These are basically these are the data rates at which it works at different clock frequencies, energy dissipation per bit, latency, etc. All these are great numbers, and it's been reported in the 2009 Kyoto VLSI Symposium. I believe it was one of the finalists for the best paper prize there, but I don't know if it won or not. This is entirely the work of Zhenya and Bora and so on. We've been involved. I personally have been involved only in the theoretical aspects of it. And Lara has been involved in some of these aspects because of she's worked with the platform there, Simulink and all that. So she's been involved in some of them. So these are the functional measurements. The airflow just completely vanishes down to 10 to the minus 14. It looks like essentially all the error is being caused by the code bits, which you cannot beat. Maximum likelihood. And in terms of the state of the art, it's truly astonishing. Logic density is about a little bit higher, but the peak throughput is 7 times what was previously reported. Power savings is 10 times what was previously reported. The error flow is 2 orders of magnitude below anything that was commercially available. So all our sponsors like Marvell Technologies, ST and all that, they love this work. And I guess that's a full story of this long 10-year project. Now, there's a lot more to be done. One of the main things that we need to do is to work all this out for the magnetic recording area. There, the fundamental difference is that the channels are no longer additive byte Gaussian. They work with something called partial response maximum likelihood channels, which involve memory across the bits, which completely changes the story for low density parity check codes, etc. So we are hoping to push some of this theory and make a parallel development in the magnetic recording space. So I think that's all.
Question. Is any service provider which is using this thing at all?
Well, so this is going to happen. All we've done is in the public domain, so it's all out there and anybody can use it.
Yeah. Now, what is the basic number of bits, the data bits that you're going to use to apply these codes to and so on? That's before encoding. I mean, what do you have in mind?
No, the throughputs are. The standard has certain throughput rates that it talks about, and we're able to hit those. I think these throughput rates are the things.
But do you have any in mind as far as the number of data bits that you're going to be using? Let's say if you wanted to, finalize this whole thing.
I think 10 gigabits per second is a good benchmark that people talk about if you read commercial news and what they mean by gigabit Ethernet. Now, for us personally, we are academics, right? Our problem. We have a problem. Problem is there was an error flow.
No, I'm talking about the word. I'm talking about the actual word, the basic word. For example, talk about the regular parity check, the common regular parity check. You have like maybe bytes, 7 bits, and then you apply a bit which is going to be the parity check.
Oh, sure, yeah. So here the numbers were buried in the toss.
So they are like 6, 7, 6 or 4, whatever,
So
right?
2048 is the block size, and 384 is the number of checks. It's buried in here. So this is in effect, if you subtract this from that, you get whatever, you get 16 something, right? So that's the number of bits, and then this gets converted into 2048.
Yeah. Now, when you compare this one with the common parity check, basically that one you can do it on the flies on one hand.
Yeah.
On the other hand, the overhead is about like 12.5% or whatever. Whereas this one now, question is that will you be able to do this thing on the fly as it's received? Will be decoded, can be decoded right on the flies, or it's going to take a lot of computation to do this?
No. So the delays that we report are actual, real numbers. These are measurements from the chip,
Yeah.
and you can see they're on the level of, I think, nanosecond. Here, so here are the numbers, right? So the latency is at these clock rates is just 960 nanoseconds. Here's 137. They're very respectable numbers.
Yeah, sort of like computers that are correct.
Yeah, they're very respectable numbers.
Okay. So how do you compare then this one with the common parity checks? I mean, you think that this is going to be, because that one was being used, for some times, but then you think that this basically is going to beat it as on because of the lower type of error things that you're going to get.
Because eventually all codes are parity check codes at some level, in the sense that you have introduced some parity checks. So I'm not entirely sure I understand the question.
My point is that compared with the other ones that we have already already there.
Oh, sure. So the thing is, this is a standard for 10 gigabit Ethernet that has already been set, and people have been building chips for this standard, and we just build better chips. So it's not as we didn't make the choice as to which code to work with. In principle, the design flow in here could be applied to any chip, but in many cases you wouldn't care because it depends on the application. For instance, in fact, you also made the point, in some applications like wireless and so on, you don't really worry about getting down to such low error rates because you could just push the problem up to a higher layer.
Right.
But in this kind of application, you can't because of the speeds involved for one thing. And in magnetic recording, you don't want your bank balance suddenly decreasing by a factor of 10. So the error probability requirements are extraordinarily stringent.
Right.
So I think the short answer is that for codes of moderate sizes in applications that are not so demanding, it's not necessary to go through this exercise because the error flow is not a real issue.
Yeah.
You really have to have a high performance objective.
And then finally, how would this one perform with the burst chips when you have a lot of these suddenly go down? Are gone.
Exactly. So those are the kinds of issues that we need to address. The things that are having to do with memory in the channel, particularly PRML is what we want to address. But bursty noise models also have that flavor. And very little is known about LDPC codes, even for moderate sizes with those kinds of error models.
Yeah, thanks a lot.
One of the things you mentioned is the fact that if you want to simulate to get an estimate of the error rate, that is a problem because the probability is so low that I couldn't, in layman terms, can you explain how you circumvented that problem?
Okay, so actually there's a whole aspect to our story that I didn't even mention. So first of all, the way we circumvented the problem here was actually twofold. One aspect of it I didn't mention. One is just raw brute force, right? I mean, if your bodyguard is weak, then you send him to the gym and he becomes more muscle. That's not what you did. That is, in effect, you just emulate the code on hardware. Hardware just runs 100 times faster than software, so you just have that much more time to get more data. That's sort of the dumb way. But there is another thing that is very important, which is an idea that is called importance sampling, which is an interesting statistical idea, widely known to statisticians, which we also used in our hardware emulation, and which we are pursuing actually at the level of simulation in some of the theory problems. So here the idea is roughly the following. It's a beautiful idea. There is some event that is very rare, namely the fact that the errors happened. But the reason it's very rare is because the noise is got a small variance, let's say. So what you might do is you might actually do the simulation with a different noise. You might simulate it with a noise which has got a huge variance, just to give an illustration, or which has a different mean, etc., which makes this event of error much more likely. Now the problem is the event is being simulated under a different distribution. But when you do your estimates, you can compensate for that by putting in a term in the likelihood ratio, which it sort of tells you that you're working with this particular probability distribution instead of the other one. So instead of just counting the number of errors, you count some function of the error which tells you how relatively likely it is. And this was also used in our.
Is this related to good Turing estimate and those types of things or not?
No, good Turing is actually more related to this issue that you don't have a model for what you're working with, right? I mean, that's this work of Orlitsky, etc. The point is you don't know what the alphabet size is, blah, blah, right? This is not the kind of scenario there, but it's a traditional statistical idea.
I was just wondering, in terms of power, you had a couple of slides. Is this power with respect to the hardware, or when you compare it, for example, with Turbo code, have you done any analysis in terms of how much you can actually save power, especially if you implement it in hardware compared to other codes?
So the power numbers are reported here, right?
Right. But
So this is the, I think the total power dissipation on chip. So it includes, it's basically, I guess, whatever the chip is burning. So I'm not sure what the question is. I talked about transmission
you can
power.
actually implement another type of, like turbo code, for example, or
Yeah.
another type of coding scheme.
Right.
Compare it with this. Do you think that there's a significant difference in terms of power?
So the power that gets dissipated is very much dependent on how you implement things, right? So design flow. We have not really done, we have not built a chip, to my knowledge anyway, for turbo codes. So I think the short answer is no. But of course there is a lot of literature out there. Many people have chips. I mean, none of these things can be compared on one axis, right? There's a performance versus power trade-off. And I think I really think the thing is, if one cannot. It seems to me that your question is motivated towards arriving at some kind of comparison between the codes on the basis of this comparison. But I don't think that's reasonable. It's really because it's not a characteristic of the underlying code.
I think what he's trying to say is from the power numbers, can you back out the signal to noise per bit for a particular code? I think if I'm not.
Well, I just think one of the big issues right nowadays is basically power saving issue.
Yeah, right. Exactly.
So I was just wondering, like, in terms of signal to noise ratio, obviously the performance of this is much better than, for example, previous coding schemes. But in terms of power usage and the power, but you're saying basically, apparently, you don't think that's a function of the coding mechanism, rather than what implementation. But because of the slipping mode that you actually introduced in this type of coding scheme, I would think that it should have, I mean, it seems like maybe you actually save a lot of power just at the theoretical level in terms of like going back and forth.
No, so I think so first of all, the code is chosen by the standards committees on the basis of some of these kinds of trade-offs that you're proposing. So I think what I might draw from your question is that one could potentially perhaps go through some such design flow for other kinds of code choices and then try to influence the standard accordingly. Perhaps that might be the right kind of approach. Now, what we've done is just shown that with this standard you can do a lot better than you could do before. We've done, and the way these numbers should be interpreted is that these are reasonable numbers. This is not considered outrageous compared to what people are used to. But we're not really focused so much on optimizing this. Mostly what we focused on actually is in optimizing the performance. There is this factor of 100 in the bit error rates. That was the goal towards which we worked, while trying to make sure that we didn't do anything outrageous on the other aspects of it. I'm not sure if I answered your question, but I understand.
Are there any other questions? All right, I would like to thank very interesting and then technical and really informative.
Thank you.